We are in Chapter 9, Inferences from Two Samples. 9.1 is two proportions. So in sections 7.1 and 8.2, we discussed inferences regarding a single population parameter, which is our proportion. And this concept used that we saw in these previous sections will be extended to include two samples now. So a hypothesis test, conduct a hypothesis test of a claim about two population proportions. And so this time instead of one population proportion, we will deal with two. And then we'll also be looking at confidence intervals that again deal with two population proportions. And remember, confidence intervals need to be set up as a two-tailed test. So since we're dealing with two different population proportions or two different samples, we need to look at independent and dependent sampling methods. So independent sampling method is when the individuals selected for one sample do not dictate which individuals are to be in the second sample. Whereas the dependent sampling method, also called match pair sampling, is when the individuals selected to be in one sample are used to determine the individuals in the second sample. Note it's possible for an individual to be matched up against him or herself. So a lot of times with dependent samples, you might have siblings or twins, or maybe it's something like a pre-test and a post-test where you're matched up against yourself. Remember, a few reminders here. So we have qualitative and quantitative data. So qualitative data cannot be expressed as a number, whereas qualitative data is anything that can be expressed as a number. And then also a response or dependent variable is the particular quantity that we ask a question about in our study. So next thing we have is the sampling distribution of the difference between two proportions. And this is independent samples. So suppose a simple random sample of size N1 is taken from a population where X1 of the individuals have a specific characteristic, and a simple random sample of size N2 is independent, taken from a different population where X2 of the individuals have a specific characteristic. The sampling distribution of P1 hat minus P2 hat, so we're looking at the difference, where P1 hat is X1 divided by N1, and P2 hat is X2 divided by N2, is approximately normal with a mean of the difference between P1 and P2 in a standard deviation. And we have a pretty intense formula here that we don't need to stress too much about just because we will be using our calculator, provided that n times p is greater than or equal to 5 and n times q is also greater than or equal to 5 for both samples. And each sample size is no more than 5% of the population size. The standardized version of P1 hat minus P2 hat to find that z-score is given, which has an approximate standard normal distribution, again with mean 0 and a standard deviation of 1. So below that, it says the null hypothesis is a statement of no difference, as always. So our null will always be P1 is equal to P2. Because H naught is assumed to be true, implies that P1 minus P2, since they're equal, if you subtract them, you would get 0. And we also assume P1 is equal to P2, which is equal to P, where P is the population proportion. So the example right below this says determine whether the sampling is dependent or independent and indicate whether the response variable is qualitative or quantitative. So part A says a researcher wishes to determine the effects of alcohol on people's reaction time on a stimulus. She randomly divides 100 people ages 21 and older into two groups. Group 1 is asked to drink 3 ounces of alcohol, while Group 2 drinks a placebo. And again, remember, a placebo is something that looks and tastes just like this alcohol that the other group is consuming. However, it's just like a water or a liquid that isn't alcoholic. Both drinks taste the same, so the individuals in the study don't know which group they belong to. 30 minutes after consuming the drink, the subjects in each group perform a series of tests meant to measure reaction times. So the first question here says determine whether the sampling is dependent or independent. And since we're dealing with people that have nothing to do with one another, this would be independent sampling. And they're measuring reaction time. And so yes, this is going to be quantitative, since we are dealing with measuring time would be numerical. Part B says a political scientist wants to know how a random sample of twins over 18 years old feels about Democrats in Congress. She obtains a simple random sample of 224 registered voters who are also twins and asks, do you have a favorite or unfavorable, and then she rotates that, opinion of the Democratic Party. Each individual was asked to disclose his or her opinion about the party, and the twins' opinions were recorded. So the first question again is determining whether the sampling is dependent or independent. And since we're dealing with twins, since I select one of those twins first, meaning I have to compare it to their twin, not somebody else's. So that dictates who is being selected in that second group. So this is an example of dependent sampling method. And the second question says indicate whether the response variable is qualitative or quantitative. And since they're asked about their opinion, it's not really something I can measure. And so this would be an example of qualitative data. On the next page, we have a box here that says hypothesis test regarding the differences between two population proportions with the TI 83 or 84 calculator. So the next thing right underneath that, it says to test hypothesis regarding two population proportions, P1 and P2. We use these steps provided that. So this is what you guys will have to check to make sure that we can actually perform our test. The first is that both are going to be simple random samples. The two samples are independent, and that is key here. So this is only for independent samples when we're dealing with proportions. And n times p and n times q are both greater than or equal to 5 for both samples. Step 1 is going to be determine the null and alternative hypotheses. So if you look again at your null, they should all be the same with that P1 equal to P2. And your alternative is going to depend on if it's a two-tailed, left-tailed, or right-tailed test. Step 2 says to select alpha, which is again normally given to us, otherwise you can select that value yourself. Step 3, go to stat, test, number 6 on your calculator, and again if it's something different, make sure you write down what it is on your calculator. It should be 2 prop z test. Then you need to enter in the values x1, n1, and x2, n2. Select the appropriate relationship between P1 and P2. Highlight calculate and press enter. When you do, you're going to get two values of importance for us that are going to be in the output. Z equals, which is our test statistic, is Z score, and P, which is going to be our P value. The testing using that P value method, like we saw earlier in the semester, is if the P value is less than alpha, then we reject the H naught, and then you can't forget to state your conclusions again. So right below this says we can also consider a confidence interval estimator for the difference between population proportions P1 minus P2. If the confidence interval estimate of P1 minus P2 does not include 0, we have evidence suggesting that P1 and P2 have different values. Consequently, a conclusion based on confidence intervals might be different than a conclusion with the hypothesis testing. Confidence intervals are always need to be set up as a two-tailed test, and that is really key here to remember. So again, that's dealing with that plus or minus or the give and take that error, and that's why they have to be set up as a two-tailed test. So to conduct a test using a confidence interval, find the confidence interval, and then if 0 is in the confidence interval, then we do not reject the null hypothesis. So if 0 is in the confidence interval, we do not reject the null hypothesis. And if 0 is not in the confidence interval, then we reject that null hypothesis. And again, that null hypothesis was saying that that difference could be 0. So right below this, we have our steps for conducting a confidence interval for the difference between two population proportions with independent samples with an 83 or 84 calculator. So to construct a confidence interval, the following requirements must be met. So again, both are simple random samples. They need to be independent. And then n times p and n times q both have to be greater than or equal to 5 for both samples. And now on your calculator, you're going to go to stat, test, and then we have b, and again change it if it's different on your calculator, 2 prop z int. And then you're going to enter those values again, x1, n1, x2, n2, enter your confidence level, and then the calculator is going to give a lower and an upper bound, and then you need to interpret your results. And to interpret your results, you need to refer to this, so definitely give that a star. So we'll keep saying this as we go through. Refer to page 2, and it's looking to see if 0 is in that confidence interval or if it's not. So we have an example on the next page that says test whether P1 is less than P2 at the alpha equals 0.05 level of significance. Sample data, x1 is 109, n1 is 475, x2 is 78, and n2 is 325. So assume that the samples were obtained independently using simple random sampling. So they tell us right away that we are dealing with independent data. And so the first thing on here, part A, says to determine the null and the alternative hypotheses. And so H0 for our null and H1 for our alternative. And it says to test whether P1 is less than P2. So we are dealing with a left-tailed test. Your null is always going to be P1 is equal to P2. So in order to do this, we need to use a 2 prop z test. So the first thing we need to do is determine part B, which is determining that test statistic. On your graphing calculator, you're going to go to stat, scroll right to test, and then find 2 prop z test. You need to enter in the values of x1, n1, and x2, n2. Make sure you enter those in correct. And then you also need to select your alternative hypothesis, which is going to be P1 is less than P2. And from that, select enter, and you're going to get your test statistic along with your p-value. And so part B for this example is asking for the test statistic. Let's go ahead and round that to 2 decimal places. So you would get negative 0.35, whereas part C on this example is asking also for the p-value, which we're going to round 4 decimal places since this is a probability. And I get 0.3649, rounding that 4 decimal places. And from the calculator, we get a test statistic of z equals negative 0.35. And we also got a p-value, which is part C, of 0.3649. And part C says determine the p-value and conduct the test. So we need to compare this to alpha, which was given to us as 0.05. And this is definitely greater than alpha, which is 0.05. And so what does this mean? This means that we do not reject H0. And we would write an actual conclusion that there is not sufficient evidence to support the claim that P1 is less than P2. So there is not sufficient evidence to support the claim that P1 is less than P2. Now part D says to construct a confidence interval appropriate for the hypothesis test in part C. So in order to do this with the confidence interval, I'm going to go ahead and draw my bell-shaped curve. And again, I want to remind us that confidence intervals always need to be set up as a 2-tailed test, like we said earlier. And since I'm dealing with a left-tailed test, my alpha is going to go in the left tail, which is over here. So this little area over here, and I'll shade it, is going to be equal to alpha, which is 0.05. However, in order to do my confidence interval, I need to have this set up as a two-tailed test. And remember, your normal curves are bell-shaped, and they are symmetric about the mean. And remember, your mean is right down the middle. And so that means that there will be another line over here if I were to make this be a two-tailed test. And that other line would have the same area also. So this would also be 0.05. So that means that that center part that's in between those alpha values is going to be my confidence level. And since the total area under the curve is going to be 1 minus that 0.05 minus the other side, which is 0.05, would equal 1 minus 0.10, which would make this 0.90 in the middle. So our C level, which is what the calculator calls it, or our confidence level, will be 0.90. On your calculator, you're going to go to Stat, to Test, and this time we're going to use 2 prop Z int. So since we are doing an interval. And the next thing that you want to do is to type in x1, n1, x2, and n2. And then our confidence level is going to be 90, or our C level is going to be 90. And when we do that, we're going to get a lower limit of 0.061, rounding that 3 decimal places, and an upper limit of 0.040 when you round that 3 decimal places. So on the calculator, we get an interval of negative 0.061 and an upper limit of 0.040. And the way to look at this and to determine if we are going to reject our null or not reject our null is to see if 0 is in our confidence interval. And again, this was written on page 2. So if you notice, we have a negative value as our lower end and our positive value on our upper end on these limits for our confidence interval. And so 0 is in this interval. So 0 is in the confidence interval. And this means, so if you go back and look on page 2, that if 0 is in the confidence interval, then we do not reject the null hypothesis. So do not reject the null hypothesis. And what you did right now is you did the test and found a conclusion using confidence intervals. And in part C, we used our p-value approach. And if you notice, we have the same conclusion. 2 different ways to conduct this test. So one was using a p-value approach, and the other one was using a confidence interval. The big thing here with confidence intervals is that they do need to be set up as a two-tailed test. So the example right below this says, a study was conducted to determine the proportion of people who dream in black and white instead of color. Among 306 people over the age of 55, 68 dreamt in black and white, and among 298 people under the age of 25, 13 dreamt in black and white based on data from Do We Dream in Color. And the article is written there, so you can look that up if you want. We want to use an 0.01 significance level to test the claim that the proportion of people over 55 who dream in black and white is greater than the proportion of those under 25. And so part A says to test the claim using a hypothesis test, and then part B says to test the claim by constructing a confidence interval. So for part A, we need to first set this up. It's a little bit different than the previous example where x1, n1, x2, and n2 are all given to us. It's a lot nicer when they are given to you or a table is provided. So for this one, we have to read it and actually figure everything out. So we're going to have to set up 2 different groups for this test. And so if you notice, we have a group of over 55 and another group of under 25. So I'm going to make my own little table over here on the side. So I'm going to say over 55 and under 25. And those are the 2 groups that we have. And I need x and n for both of these groups. So the first thing is that it says that among 306 people over the age of 55, so that would be 306 here for my sample, it says that 68 of them dreamt in black and white. So that would be my X value. And then likewise with the people that are age of 25 and younger, it tells us that we sampled 298 of those. And 13 of them dreamt in black and white. So that would be the X value for that second group. And so I'm going to go ahead and call this P1 and this one P2 when I talk about proportions. And so my null and my alternative, my null is going to be that the two proportions are equal to one another. And we know that we are dealing with proportions because the problem tells us that. And then we also need to be careful when reading the problem that you notice the symbol that needs to go in for the alternative hypothesis. So it does say that the proportion of people over 55 who dream in black and white is greater than those who are under the age of 25. And so we know P1 is our older group, and that is going to be greater than our younger group, which was P2. On your graphing calculator, we are going to go to Stat, to Test, and go down to 2 prop Z test. And then you need to enter in X1 and N1, which is for the group that are over 55, which is how we set up this problem, and then X2 and N2, which is our under 25 group. And then our alternative hypothesis is going to be P1 is greater than P2. So make sure that you have that selected for your alternative hypothesis. From there, you will get your test statistic, which is Z, and you also get your p-value, which if you notice, it would round to 0 because it's 5.98 times 10 to the negative 11th. So from the calculator, we have a value, p-value of 6.01 times 10 to the negative 11th, which if you round 4 decimal places will give you 0.0000, and this is less than alpha, and alpha was given to us up above is 0.01. And since our p-value is less than alpha, this means that we are going to reject H0. So in conclusion, we can say there is sufficient evidence. So there is sufficient evidence at the alpha equals 0.01 level of significance to conclude that, and it's to conclude that the proportion of people over 55 who dream in black and white is greater than the proportion of those under 25. So the proportion of people over 55 who dream in, and I'm going to go ahead and put B and W for black and white, is greater than those under 25. So part B says to test the claim by constructing a confidence interval. And so again, for this problem, I'm going to go ahead and draw my bell-shaped curve. The reason why I do this is so that way you can remember that with confidence intervals, you need to have this set up as a two-tailed test. And since this time our alternative hypothesis is P1 greater than P2, I know that I am dealing with a right-tailed test. And with a right-tailed test, that means that this is going to be our alpha value. And alpha for this problem is equal to 0.01. And again, looking at this, this is not set up as a two-tailed test, meaning I need to make it be a two-tailed test. So I'm going to put another little line over here since this is symmetric. And this shaded area that we have over here would be the same, would also be 0.01. And so that means your total area under the curve is equal to 1 minus 0.01 minus 0.01 would be equal to 0.98. And so our C level, or confidence level, is going to be 0.98. On your calculator, you're going to go to Stat, to Test, and go down to 2 prop Z int, and you need to enter in the values of x1, n1, x2, and n2 for this problem. And then our confidence interval this time is going to be 98, or 0.98. And then once you have that, select enter, and you should get a lower bound and an upper bound. We're going to go and round both of those to 3 decimal places. So from the calculator, we get an interval of 0.117 and an upper value of 0.240. So our lower limit is positive and our upper limit is positive. And so this means that 0 is not in this interval. So if you look back on page 2, if 0 is not in the confidence interval, then we are going to reject the null hypothesis. Or H naught. And so if you look at your conclusion that you would have had here, which is reject your null hypothesis, we had the same thing in part A. Again, one's using that p-value method and the other one is using a confidence interval. So part C says an explanation given for the results is that those age 55 and older grew up exposed to media that was mostly displayed in black and white. Can results from part A and B be used to verify the explanation? And no, we cannot say just because this is showing that we're rejecting our null, which is rejecting the fact that those proportions are the same, we can't say it causes anything to happen. We can't say that because they were exposed to media that was mostly in black and white, we can't say that this caused it to happen. So association does not imply causation. Remember that from earlier this semester.